Hello, in this video I want to talk about paper 1 for May and June 2025 and what I'm predicting is going to be in the exam. Okay, as you are aware, paper 1, an hour and 45 minutes, and we're focusing on the sort of theoretical side of computer science. 50% of the final marks, total of 75 marks. Okay, will be done along with paper 2, which is exactly the same, an hour and 45 minutes. 50% of your final mark is from paper 2, okay, IGCSE. So here we are, off we go, May, June 2025. You must answer all the questions on the exam paper, unless you don't know it. Please have a guess, please have a go. As always, there is no calculator on this paper. So, where are we at? Well, depending on where you are in the world, okay, your exam, if you're in Europe or Africa or even the Middle East, you'll be in zone 2. Okay, even anywhere from between the UK and I would say Oman or Saudi Arabia, yeah, would be in zone 2. Zone 1 are the Americas. I'll show you this, but basically the start on the paper 1 starts on the 12th of May in zone 1, 13th, and goes right the way through. If I show you this, you can see here, zone 1, the Americas, Europe, Africa, Middle East, zone 2, Asia, zone 3, Sri Lanka, Thailand, etc. Zone 4, Asia Pacific, so you've got the Australias, you've got Brunei, Malaysia, and then zone 5 is places like Fiji and the Marshall Islands and parts of New Zealand. Okay? So, what do we predict? What do we predict? As you can see, binary and number systems. Binary also including hexadecimal conversions to its complement for doing minus negative binary numbers. Data representation, a little look at compression, file sizes, why we do need compression in terms of file sizes, why we need compression in terms of using files and sending files across the network, file sizes, sample rates, network concepts such as packet switching, error detection methods, and network components, storage, primary, secondary, and USB storage, logic gates and truth tables, system architecture such as for Neumann and fetch, decode, and execute cycles, software types, firmware, application software, operating systems, security such as firewalls, encryption, knowing a little bit about phishing, farming, hackers, okay, ransomware maybe. But these are the main, from the last 5 papers, these are the things that have come up the most frequently, okay? Done a little bit of sort of data analysis, and these are the things that have come up most recently. Finally, automation and sensors. There's always a question on sensors, and it's usually quite a big question, okay? Use of microprocessors, ADCs, DACs, yeah. Okay. Question styles. Yeah, define and identify simple recall-based questions, 2 and 3 marks. Calculation-based questions, binary hexadecimal conversions, file size calculations, diagrams. This could be circuit representations, i.e. what's inside a CPU, or it could be, let's say here, with the fetch, decode, execute cycle, but it could be, and you don't have to do these, I do recommend them, diagrams to explain sensors, maybe a diagram of a greenhouse, something like that, where sensors are going to be in operation. Explain and describe questions, extended questions with multiple steps, explanations. These could be bullet points, okay? 3 to 6 marks. And finally, fill in the blanks. These have been introduced in recent years, and you have a bank of words, and you've got to put the correct word in the correct space within a paragraph of text. Okay? So there we go. Logic circuits and encryption have popped up in recent times relating to that. So, given the recurring trends, binary systems and logic, network and security, packet switching, firewalls, yeah, real-world applications, microprocessors, sensors, automation, Emerging trends, I would have thought this is going to come up. Artificial intelligence, robotics, cybersecurity, and then something a little bit about, again, the fetch, decode, execute cycle, von Neumann architecture. Okay. Okay, so we'll switch to the board. We'll have a little look at some practice questions, which I believe will come up in terms of paper May, June 2025. So, convert the following denary numbers to 8-bit binary and hexadecimal, 25, 150, 200. Can you remember how to do this? Well, let's first of all convert to 8-bit binary. So what I'm going to do, I've got the pen working, yeah, 2, 4, 8, 16, 32, 64, 128. Will give us an 8-bit register. 1, 2, 3, 4, 5, 6, 7, 8 numbers. Now, fairly straightforward to convert to binary. We need to work out how many do these numbers go into the number that's specified, i.e. 25. Well, 128 does not go into 25. Okay? Neither does 64, neither does 32, but 16 does. And with that in mind, 25 minus 16 would leave us with 9. So 1, 8, 9 take away 8 would be 1, so that would be no 4s, no 2s, and 1. Okay, so the 8-bit number is 000110001. Okay, so 16 plus 8 is 24, plus 1 equals 25. Okay, so equals 25. And then the nice thing about binary is, if we were converting this number into hexadecimal, 25, 150, and 200, if I split this, yeah, if I split this as 2 nibbles, on this side I've got 1, and on this side I've got 9, yeah? So these sort of change to the same as this, 4, 8, 2 nibbles, so I've got, sorry, 1 lot of 1, there's no lots of 2, no lots of 4, no lots of 8, okay? Nibble 1, nibble 2. And this side I've got 1 lot of 8 and 1 lot of 1. So my hexadecimal number would be 19, okay? So let's do 150 really quickly. Put these numbers in. 1632, 64, 128. Now 150, obviously works in a different way. We've got 1 lot of 1 to 8 does go into 150. So what's left over? 150 minus 128 would give us 32. Okay, so that's that 32. 32 plus 128 equals 150. So no, 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 no. Okay, again, if we do the split, yeah, we turn these into our second nibble. 2, 4, 8. I've got 1 lot of 8 and 1 lot of 2, which will give me 10. Okay, and I've got nothing on this side. Okay, but what's 10 in terms of hexadecimal? Well, once we get past 9, 10 would equal A, 11 equals B, 12 C, 13 D, 14 equals E, and 15 equals F. Okay, so that is our number, yeah? So here, you can see we would have A0 would equal 150. Yeah, 10 15s. Yeah, 10 15s equals 150. Of course it does. So next one. Okay, this time we've got 200. So that was number 200. Okay. Obviously 1 lot of 128 in 200. But how many is left? Minus 128. Okay, would give us 72. Okay, so that must mean 64 does go into 72. Yes, it does. How many is left over when we take away 64 from that? It would leave us with 8. Okay, 64 plus 8 equals 72. So 0, 0, 1, 0, 0, 0. Again, we're going to split this into two nibbles, like so. It's just going to change the C now. 1, 2, 4, and 8. Okay, so here I've got 8 plus 4 equals 12. And here I've got 8 on its own. So can you remember from last time? 12 would equal A equals 10, B equals 11, C equals 12. So 12 would become C8 would be our number. Which basically means, if we put a 16 and a 1 down here, basically means there are 16, so there's 12 lots of 16 and 8 lots of 1s. 12 16 is 192, yeah, 192, and of course, plus the 8 would equal 200. Okay, so that's how we do that, nice and simple. Yeah. 2's complement, minus 50, minus 12, and 1. Now I've put some notes down here. Step 1, write the positive binary value. Step 2, invert the bits. Step 3, add 1. I'll do the first one, and we'll see if you can maybe have a little think about the next two. So 1, 2, 4, 8, exactly the same as before. 16, 32, 64, 1, 2, 8. Okay, and I've got to find 50. So we're finding the positive value. Okay, 50. Obviously, they're no good. 50 doesn't go into either of those two, or they don't go into 50, but that does. Yeah. So 32, if we add 16 to it, we get 48. We need 50. So we're going to go 0, 0, 1, 0. 16 plus 32 is 48, plus 2 equals 50. So that equals 50. So now what we need to do is invert the bits. So 1, 1, 0, 0, flipping them up. 1, 1, 0, 1. Okay, so flip them, but now I've got to add 1, yeah, to the inverted value. So here I'm going to go plus 1. Okay, so 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, and then these should, because we're not adding anything to them, remain the same. So that is our negative 50 equals that. You must make sure that you're specifying that it is a 2's complement negative value. Next one, negative 12. 12, positive value, 1, 1, 0, 0, 0, 0, 0, 0. Plus 1, yeah, will give us 0, carry the 1, 0, carry the 1, 1, 0, 1, 1, 1, 1 will give us negative 12. Okay, and then finally, negative 1. Well, let's get positive value 1. Let's put all these in, like so. Now if we flip it, and I add a 1 to it, yeah, you can see that the number is going to be all the 1s. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Now, all the 1s generally would add up to 255. Yeah. Or a full 8-bit register, massive number of 255. You might know that you may know that from doing hexadecimal values. But this is basically the same, yeah, as negative 1. Okay, class done. In terms of the firewall, explain how a firewall protects a network from threats like malware and hacking. I've written some things down here. What is a firewall? Acts as a security guard for your computer. It watches the information coming in and out from the internet and decides what is safe to let through and what should be blocked to protect your computer from hackers and viruses. Perfect. Okay, perfect. That would get you the full marks. Should do. But what is also nice is 1 bullet point this. If it's worth 4 marks, let's try and get 4 bullet points from that. And also, but if it's worth more marks, maybe something, not the best picture in the world, Europe, Africa, okay. We could do the internet, www, yeah, and that's sending information, or it's been we're requesting information from our computer at this end. Let's call it, yeah, user. And we've got a firewall. Okay. Fire. So this is what's happening, but we might have some bad data coming in from the internet, and we might also have some good data. Okay. The firewall stops, is blocking harmful data. Maybe a hacker. Okay, blocks. Well, this one, data. And this is allowed through, and obviously connects to our hub at home, yeah, which is sending various wireless signals, or it could be connected to our computer. So our mobile phone, different devices can access receiving information. So yes, World Wide Web, hackers are blocked, blocking of harmful data, yeah, anything suspicious is going to be stopped by the firewall. The firewall, you can also request the firewall blocks certain websites. If there are children at home and they want to put a parental lock on, or the parents want to put a parental lock on, they could use the firewall as a block of certain websites. So that's basically how that works. Some information, yes, do it as bullet points. A drawing is always good as well. Okay? Okay, now we've got usually an 8-point question, a scenario-based question. Okay? A farmer uses a microprocessor to control irrigation. Describe how sensors and automation are used to maintain optimal soil moisture. How do we keep the earth, the soil, the ground, where our plants are, how do we keep that wet? Okay, so the plants can grow. So I've put a little thing on here, just as a recap. What is a sensor? You can see here we've got a thermometer, the type of sensor. Okay, but the sensor on the thermometer is saying basically when this reaches 50 degrees, okay, say it's centigrade, say that it's too hot, yeah, and give us a warning message to say it's too hot. Okay, so a sensor is a device that detects and measures physical properties in the environment, such as temperature, light, or motion, and converts this information into data that computers can understand and process. Okay, so how are we going to do it? We've got our garden down here, okay, with our flowers. Try and draw a nice picture. Yeah, flowers. Yeah, and in there we've got some sensors. Moisture. Okay, there. So these sensors are connected to, first of all, something called an ADC. Yeah, an ADC, an analog to digital converter. Okay, and this, let's go wild, this up here is connected to our microprocessor. Okay, so, and the microprocessor is also connected to, down here, our water reservoir, it's coming from the board, and water. So this, yeah, this cycle here is continuous. continuous sending data. Continuously sending readings from the sensors through the analog to digital converter, continuously sending data to the microprocessor. The microprocessor has a range, holds range of data values. Okay, so let's say the temperature is anywhere between e.g. 1 to 5. Okay, so long as the water is anywhere between 1 and 5, as long as the water level is anywhere between 1 and 5, this is okay. But if the data that's coming drops below or even above, so it's too wet, or generally speaking for this one, it's going to be too dry. If it drops below 1, then we need to send a signal. Send signal to, and we should have learned this word, actuator. Okay? Actuator controls flow of water. Okay? So, simplified drawing, but we've mentioned what sensor is. So we've got sensors that are sending data through an analog to digital converter. This is continuous to a microprocessor which holds a range of information. Whilst the range is okay, this continuous cycle just keeps going and going and going. But problem, if less than 1, for example, send a signal to the actuator. Okay, the actuator controls the flow of water. Water turned on. Once it's back to its required level, signal goes okay, the water can be turned off. If okay, water off. And that's a continuous cycle. So 1, 2, 3 for continuous, 4 for microprocessor, holding data, 5, if there's a problem, 6, actuator, 7, water turned on and off if it's okay, 8. Usually an 8-mark question, that should get you 8 marks. That should get you 8 marks, okay? Okay, last question, logic design question. Design a circuit for the statement X equals, parentheses, parentheses, A or not B, parentheses, and C. Okay? Simple statement using 3 gates. You need to know 6. The AND gate, the not AND gate or the NAND gate, the OR gate, the not OR gate, the NOT gate, and then the XOR gate, which X basically means absolute OR. Not AND, like the OR gate, or basically is OR and AND. XOR is only when it's one or the other, not both. So, we've got the easy ones. We've got the OR gate, the NOT gate, and the AND gate. And because these are in parentheses, we're going to leave that as part 1. Put that in, part 1. Yeah, this can be part 2, and C can be part 3. Okay, so we're going to start with X. We're going to put X over here. Okay, and then we've got 3 inputs, A, B, and C. So we're going to put A here, B, and C. So where do we go? This AND is on its own. Okay, so we're going to take this AND and we're going to put it here. Okay. So we've put the AND gate, and this is feeding into the X. Okay, so what feeds into the AND gate is going to be basically this and C. Now C has got nothing else attached to it, so we can put C directly to the AND gate. Okay, but here we've got A or not B. So let's take the first one, the OR here, the OR gate here. Okay, and we're going to feed that into the AND gate. Yeah, but we've got A or and then we need a NOT gate here. Okay, A or not B, and C. Okay, so that's the basic circuit. What you may find from this though, it's usually in two parts. We've drawn the circuit nice and easy. You've probably got anything between 3 and 5 marks for that. But to get another 5 marks, sometimes even 8 marks, you would create something called a truth table. Okay, this is where we draw a table with the 3 inputs, A, B, C, and we need to determine what the output's going to be based on what these inputs are. So because there's 3 inputs, we're going to have 8 different possibilities for what the output's going to be. What do I mean? 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and then we go with the 2s, 0, 1, 1, 1, 0, 1, 1, 1, 0, and then finally all 3 ones. And that should be 1, 2, 3, 4, 5, 6, 7, 8. Okay, I've left a gap here because on your exam pages it will generally say working space, working area. Now most people don't like using working area and then they get confused and it doesn't work. I'll show you why we need working area. So, if I do AB and I do after this first gate here, this NOT gate, I'll put D in here, and then I'm going to put E here after the OR gate. So what we need is C and E to be on in order for X to be on. Okay? But let's do D first, because D is basically the inverse of B. So pop D in here. So every time B is off, D will be on, and vice versa. What do I mean? 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. Okay? So half and half again, 4 ones, 4 zeros. And then we've got E, which is basically when either A or D or both are on, yeah, E is going to be on. Okay? So let's have a little look at E. So E is the equivalent of A or D. Okay? So in this case, D's on, so E's going to be on. D's on again, E's going to be on. A, no, no. Both are on there, none are on there. Yes, yes. 1, 2, 3, 4, 5, 6, 7, and 1's across the bottom there. Okay, so that's that. Yeah. Now we need to work out what E and C are. If they're both on, great, this will be on. So we're going to be looking at these two. Yeah, C and E, both. Okay, so C's off there, so that must be off. C's on, E's on, good. All off. 1 on, 1 off. 1 on, 1 off again. They're all on. All right, 1, 2, 3, 4. Yeah, they're both on. Off. Yep, and they're on. So 1, 2, 3. Okay. 1, 2, 3 different variants based on this circuit will give us positive ons at the output X. Okay, that is it. That is it for this video. So good luck with your exams, and I will see you next time. Thank you very much indeed. Bye for now.
Please continue to ask questions, leave your comments, hit notifications, and please subscribe. And finally, if you wish to buy me a coffee, I'd be truly grateful. Please visit buymeacoffee.com/learning zone. Thank you very much indeed. See you next time. Bye for now.